Hey guys, welcome back. We are almost done with this unit. Today we're just going to be reviewing pooling, which is what we talked about yesterday. Tomorrow we'll do a practice test, and then the first day back of next week we'll do a review of the whole unit, and then the second day back in person of next week we'll do the test. That test will replace your quiz score, so if you haven't done the quiz or if you didn't do as well in this quiz as you wanted to, just practice and make sure you're caught up with your homework and do well on the test and replace your quiz score anyway. So we're going to be looking into the question of what is the best way to quit tobacco. Specifically, does assigning somebody to go to support groups, does that help them quit tobacco? So they designed an experiment where they took 294 participants. They randomly assigned them into two treatment groups. One of them were assigned to regularly attend support groups. The other one was not supposed to go to any support groups, so they just kind of did it by themselves. So the random assignment, we had 143 in the support group and 151 that were in no support group. Notice that this does not have to be an equal half. There's going to be differences in the variation between the two, in the standard deviation between the two, because smaller samples are going to vary more than this one. But since we're doing the Pythagorean theorem of statistics anyway, we can really account for both of those, so it doesn't really matter. You don't have to make it an even split, which is kind of cool. Then our response variable at the end is whether or not they quit. So what proportion were successful? So we had 46 out of 143 out of the support groups that were successful, and we had 30 out of 151 out of those who were not a part of a support group who were successful in quitting. So just as a quick review of experiments, the whole key point of an experiment is not that we randomly select the participants, but that we randomly assign them into treatment groups. We want to make sure that if there were any lurking variables or confounding that was underlining that could kind of skew our results in towards one direction or something like that, that the random assignment is going to take care of that. So it's not like we have people who were highly motivated, got to choose that they wanted to be in a support group, and maybe people who weren't very motivated to quit we're going to put in the effort. So they don't get to choose what group they're a part of. We have to randomly assign them into it. Our subjects are also sometimes called experimental units. However, whenever we're dealing with people, we call them participants, not subjects or experimental units. They're not lab rats, they're people. The factor or factors, in this case, we had one factor, which was the support group. That's the only thing we were looking at, not like support group in exercise or anything like that, just support groups. You can say that we have one factor with two levels, whether they were a part of a support group or not, or you can consider this the control. Then we just had one factor at one level, and then the no support would be the control. Our response variable was whether or not they were successful in quitting, specifically the proportion of those that were able to successfully quit. So 46 out of that and 30 out of that. So let's go ahead and put this right in the calculator, which is what you really need to know how to do, and interpret it. So we'll go to stat, test. We're going to do a two proportion z-test, which is our sixth option. Now our larger proportion should be the ones that are in the support group, or at least that's what we're expecting. So we're going to put that one, that proportion first. So 46 out of 143. And then for the second one was 30 were successful in quitting out of 151. Now we have to decide if this is going to be a one-sided or two-sided test. We don't want to know just if it's different. We specifically want to know if support groups are beneficial, because why would we spend more time if support groups were not beneficial? So we want to know that the first proportion is greater than the second proportion. So it would be a one-sided upper test. Then we want to hit calculate. Lots of information here. So again, we're saying the first proportion, which was support groups, was greater than the second proportion. Our z-score, which was telling us that our observation, the difference between the two proportions, was 2.4 standard deviations above the mean, which if anything above 2 standard deviations would be considered unusual, but we want to actually quantify that with a p-value, which is the next thing they give us. So 0.8% or 0.008, that's going to be less than even a 1% alpha level, which is typically the strictest that we would use under normal circumstances. Certainly less than 5%, which is what we would default to. So this would be a statistically significant observation. The difference that we saw between the support group and the no support group, the proportions between those two, was statistically significant enough for us to be able to reject the null hypothesis in favor of the alternative, and suggesting that the support groups are actually beneficial in helping you quit. They'll give you the sample proportions for each. So of those who were in the support group, 32% were able to quit, but only looks like 20% of those who were not in the support group were able to quit. So that difference of 12% was statistically significant. The p-hat is going to be the pooled value. So the pooled proportion, if we took all the people who were in all 294 participants and all the people who were able to successfully quit, which is 76, the 76 out of the 294 would give us a total proportion, or a pooled proportion, better way of saying it, of 25.85% of all participants were able to quit. That would come into play. In fact, we actually use the pooled proportion whenever we're doing our hypothesis test, because the p-value that we have here is calculated on the condition that the null hypothesis was true. And if the null hypothesis is true, that support groups are not any more beneficial, then we need to use the overall pooled proportion instead of the individual sample proportions. Then here we have our two sample sizes for our support group and for the second sample, which was 151. All right, so that's a lot of information that they're giving us. As long as we know how to interpret that, you should be good to go. You also need to go through your conditions as well, so we'll do that in just a second. Here we go. So just as a bit of a review of Chapter 3 stuff, we had observational studies and experiments. Observational studies, or surveys as well, are kind of looking passively at what trends are we seeing in nature. So typically we actually start out the whole scientific process by looking at trends and making a conjecture or making a hypothesis about what we think is going on. And then we carefully design an experiment in order to be able to control for outside factors, be able to isolate the variables, and then do random assignment of treatment groups so that we can control any influences of outside variables like lurking variables or any confounding variables as well. So the key for an experiment is random assignment. Remember, in observations, we can show there might be an association between things or some trends going on, but we can't show that there's a causal relationship unless we have a carefully designed experiment. When it comes to observations, there are two different types. We have a prospective observational study and a retrospective. So prospective is whenever they're idealed, so we select candidates and then we have them carefully log whatever exercise and diet or whatever we're interested in as they go, and then at the end we observe what they naturally chose to do and the outcomes, whether or not they develop some disease or whatever. But oftentimes we actually have to use retrospective studies because we're dealing with rare diseases, and we can't just expect a group of 200 people or 200 participants to go about their lives and develop a rare disease, and then we figure out what they did that we think might have caused the onset of that disease. Instead, what ends up happening is we find people with this rare condition, and then we try to go back and ask them questions about what they did. Maybe a lot of them were drinking the water in Michigan, or perhaps they were from a coal mine or something like that, or around Kiev, Ukraine, or something like that. And then we can try to make connections between their environment and what's going on and what we think happened. So anyway, those are all observational studies. And then what we have here is an experiment. So we are taking people, not necessarily randomly selecting them, but we are randomly assigning our participants into treatment groups. Our next condition we have to check is the independent group assumption. So we don't have to check whether or not it's the 10% condition that we're sampling less than 10%. That doesn't matter with an experiment. That's really just for surveys. But we do have to check for independent groups assumption. So we do have two groups here that we're comparing the proportions to. One is those who were in the support groups, and the other was the treatment group that did not have support groups. So these two groups, we need to make sure that we believe that they're independent of each other. Now the reason for that is because the Pythagorean theorem of statistics, whenever we're taking the sum or difference of two proportions or two random variables or events in the first place, we have that whole thing is based on the assumption that the two groups are independent. Just like the Pythagorean theorem requires us to have two right triangle, or two legs of a right triangle, I should say. We need to make sure that we believe it's reasonable that these groups are independent. So the main thing that makes sure that these are independent is the random assignment of the groups. We don't just let people who want to be a part of the support groups go to support groups, because those people probably also had more drive to actually quit and probably would be more successful anyway. So that would be an example of some confounding. So we need to make sure that they're all independent. Also, we wouldn't want to do this by families, or if they were related, or if they were roommates or something like that, or even friends, because if one of your friends messes up, then maybe that you'd be more likely to relapse as well, or something like that. So we want to make sure that there's random assignment. That should take care of the independence. So it's reasonable for us to believe that two groups are going to be independent of each other. All right, so now that all of our assumptions and conditions are good, we can actually carry on. So we ended up with two different sample proportions. We have those that were in the support group and those who were not in the support group. Notice that we have a slightly larger standard deviation for the group that were in support groups because they have a smaller sample size. So all samples vary, but smaller samples vary greater. So that's okay. We're basically going to be looking, and then we have our difference between the two sample proportions of their success rate of quitting. So we look at the difference between those two sampling proportions. We got 12.3%. Do we think that could have occurred by random sampling variation, or is it statistically significant? So the real question we have to answer is, what is the standard deviation for two groups of these two sizes, and the sample proportions that we get between those? So first, let's write our hypothesis here. So the null hypothesis that there's no difference or no change is that the difference between the proportions, or sample proportions, there should be hats between those, or no, the true proportions, because that's what we're going off of here for our null, is that the difference between the true proportions between those in a sample of a support group and a non-support group is 0, meaning there's no difference, and that there's no effect of being in a support group, even though we probably don't think that's right? So there's no difference between quitting smoking rates and among those who are attending a support group and not attending a support group. Our alternative, instead of doing a two-sided where we're just saying there is a difference, whether positive or negative, we want to specifically say if we're going to spend time and money going to support groups, we want to make sure that it's actually beneficial, just like producing a drug or something. We're not interested if it's less effective than placebo. We're strictly interested if it's more effective than placebo. Otherwise, it's not worth approving or spending money on or anything like that. So we're going to say that the difference between these two is a positive difference. That would mean that the support group proportion or success rate was greater than that of not those who are not part of the support groups. So in other words, that support groups actually help you quit. All right, so we have our two sampling distributions for both of our different samples. We have our 143 participants. Oh, so what's going on here is I'm actually pulling this together. So this information, the pooled proportion, actually is this right here. It was the same thing as adding the total number of people who were successful in quitting divided by the total number of people or participants in our study. So if the null hypothesis states that we don't think there's a difference at all, and we're calculating p-value based on the assumption that there is no difference between the two, then we actually have to pull them together. And the only difference now is not going to be that one is with support and one did not have support groups. It's going to be that it's just a smaller sample of participants and a larger sample of participants, because if we said the support groups didn't change anything at all, then they would be exactly the same. So we need to go ahead and average them, a weighted average of them together, pulling them together is what we really call it, in order to have our largest sample, our best estimate of what the true success rate for quitting smoking, regardless of whether or not you're part of a group, which we would say our best estimate from our largest sample of the 290 some odd was 25.85%. So that's where we put in our pooled proportion in Q, pull P and pull Q there, and the small sample and the large sample. Notice the small sample has a slightly larger standard deviation, not much, but that's okay. And because these two are independent events, what we're going to do is do the Pythagorean theorem of statistics. So they should be like that, and then that will give us a difference between the two, which should look like that. So if we do this squared plus this squared, that should, and then take the square root of that, that should give us 5.1% of a difference. Okay, so we observed a difference of 12.3 between the two proportions, and if it was really the same, then the difference between those two sample sizes should have been 0 with a standard deviation of 5.1. So the observation that we had of 12, which is just about over 2 standard deviations, we can actually find the z-score, but that's actually done for us already. It was 2.4. Okay, so we should be 2.4 standard deviations, so 1 standard deviation above, 2.4, something about right there, which would give us a p-value of 0.08, which again, the calculator gave us that as well. So that p-value is basically, if we shade in this region here, let me use purple. So this area right here, this p-value is in the top 0.008%, which is much less than the top 5% or even 1% if we used a really strict alpha. So certainly we would have enough evidence to be able to reject our null hypothesis in favor of the alternative, stating that we believe that support groups are actually beneficial in helping you quit. So looking at our null hypothesis and our alternative again, as we said, we believe there is a difference, that the support groups actually do help you quit. So if there was no difference, then we would expect for this distribution to be filled in as we take millions and millions of samples, meaning there would be no difference with a standard deviation of 5.1 between difference of just two groups of a smaller sample size of 140 whatever it was and 151 I think there. So anyway, that's the standard deviation we'd see for that. We selected our alpha level, we put it at 5% here, and then 5% of the time if we had anything that was over 2 or it looks like about 8% difference between the groups, then we would have accidentally said that perhaps if it was in the right direction, if it was 8% in the other direction, then it wouldn't have mattered. But if we were in the top 5% of all of our samples, with about an 8% difference between a positive difference between the support groups and not, then we would have committed a type 1 error, which could happen. Now, if we didn't want that to happen, we could put it in the stricter 1 percentile, which would mean we'd have to have a difference between the proportions of maybe about 11%, and we had a 12% difference. So we would have been able to do that successfully or it would have been a type 1 error, it just depends. Now, if there really is a difference, and support groups do help, like they probably do, then it really just depends on what the effect size is. So what is the difference between those two proportions? The true proportion, which if we looked at all the people who have ever tried quitting smoking, all the people who were in support groups, what proportion of them were successful, and all the people who didn't go and just Lone Ranger did or whatever, and what percent of them were successful. If we take the difference between those two population proportions, let's say that the actual difference is, let's say 15%, which is even more than what we measured, then the power of the test would be the ability for us to be able to detect that. So anything that was beyond that significance level of 11% would have been able to do that. And this distribution, no longer this one here, because we said that there really was a difference and the true difference was like 15%. So now it's centered at 15%. This would be the sampling distribution model that would be filled in by our millions and millions of samples or millions and millions of experiments as we went over and over and over again between the differences between samples of those two sizes. All right, so the type 2 error would be failing to detect that. So that would still happen. If we wanted to reduce the type 2 error, we either increase our sample size, or we could even increase the alpha level, which is the same thing as like decreasing the level of significance, because or decreasing the burden of proof, however you want to say it. I know that seems kind of odd, but it looks like at this point we would have about a 5% type 1 error and 5% type 2 error, which is pretty good, I suppose, meaning 95% of the time we would have been able to successfully detect the difference, and we were able to in this case as well, because we had a sample a difference between of the two of about 12%, which would have been beyond the 11% significance level, wherever I put it. Even if it was here, we had 12%, we would have actually been able to detect it, but it was close. I mean, if it was even less than the 12% that we had, like if it was about 10%, then we would have failed to have detected it just because of that. So really, we got small samples, so we can't expect to have a very powerful test with such small samples unless there's a large effect size. Now, if the actual difference between the two was even more, like let's say 22%, then regardless of what, even with our small sample size, regardless of what strict alpha level we set, we're still going to have a very powerful test that will be able to detect that because there was such a large effect size. So hopefully by the 15th millionth time that we finally have gone over this stuff with all these beautiful things, you're finally starting to piece together the difference between a false positive, a false negative, the power and the effect size, a null and alternative hypothesis, and statistical significance, p-values, z-scores, oh my goodness, and all the other stuff. And we're not even done. So now that we said that there is a difference, the next logical question we would ask is, what do we think that actual difference is? So once we believe that there is a difference, we're no longer basing our assumptions that that there is no difference, so we need to pull them together. Okay, this is just for hypothesis testing. Okay, and the reason we do that for hypothesis testing is because it's based on the assumption that H naught is true. All right, so if H naught is not true and we believe that there is a difference, then now we need to actually use these sample proportions that came from our two different treatment groups. So what we're going to do is go to stat, go to test, towards the bottom, bravo, 2 portion z interval. It's already there for us, which is lovely. Then hit calculate. So we believe there with 95% confidence that the true difference in the proportions of success rates between those who are part of support groups and those who are not part of support groups, wow, that's a lot, is anywhere between a positive 2.3% and 22.2% difference. So that's the information that we would bring to the table, and we would probably put that information on the flyer for our support group, saying that we believe that there's anywhere between a 2.3 and a 22.2% with 95% confidence. Of course, we'd always tell that information. Difference between those two rates, proportions of this, if you actually go to the support group. So kind of nice. So how is that calculated? Well, we found the standard deviation. This was not, it is standard error still because it's based on our sample proportions, but it's no longer pooled. It's using the actual differences, which is our best estimate at that point. It is a slightly Well, it's actually about the same. Our standard deviation that we have here, it looks like. I need to update that. Should be the same there. But our best estimate for our biggest sample that we had was 12.3, and we go over critical value of, let's say, 1.96 standard deviations, or standard errors in this case. So we take that number times that number, we add it and subtract it to both, and that's how we got the confidence interval that we did with that range. So the 2.3, somewhere about there, and a little bit less than 22.5. Okay, yeah, that's it. All right, so our conclusion, with a p-value less than 1% or less than 5%, whatever alpha level we selected, it was statistically significant, so we were able to reject the null hypothesis in favor of the alternative. So our alternative was that support groups were actually beneficial in helping you quit. Our best estimate between the two difference was 12.3%, but we know if we did this experiment again, we certainly get something different than 12%. So we don't think that's the actual true difference in the population proportions. So instead, we have to give a confidence interval centered at that value with a margin of error going in both directions for whatever level of confidence we have, 1.96 standard deviations or standard errors going both directions like we did. And that's where we got the difference between those two confidence intervals. Whew, fun stuff. Oh yeah, I couldn't resist. I forgot to put this joke in there. So this is Big D's first AA meeting. Get it? Double A. See, they're all double A batteries. But not Big D. He's a Big D battery. It's pretty funny. You got him. That's funny. I'm the only one laughing, but that's pretty typical. Still worth it. All right, number 17, prostate cancer. There's been a debate among doctors of whether surgery can prolong life among men suffering from prostate cancer. Women, you don't have a prostate. Sorry. You have other types of cancer you have to worry about, though. All right, but not prostate cancer. A type of cancer that typically develops and spreads very slowly. Well, that's good news. Recently, a New England Journal of Medicine published the results of some Scandinavian research. Men diagnosed with prostate cancer were randomly assigned to either undergo surgery or not. Time out. Do you see the ethics of this? All right. So if we think that surgery is beneficial, but we're going to put them randomly assigned into either whether they can or cannot be and have surgery. So if we think that surgery is beneficial, but then we have to have a control group that's not allowed to have surgery, you see the ethical issues with that? Might I also point out that in other countries that have a certain type of healthcare, oh, I'm so controversial, you're now no longer allowing people to make the decisions on what they can do or what they can afford. Instead, you have panels of people, because it's all pooled resources, that decide whether or not you can have certain surgeries or procedures, and like they bar you from doing it. So you actually end up having to leave and go to a different country, like our awesome country, by the way, in order to have that procedure. Even if you have the money to pay for it, they still will not let you do it. So keep that in mind. There are ethics behind this, and whether or not that is pretty jacked up. So if we think that surgery is beneficial, somebody has the money to pay for the surgery, who are we to say that they can't have a surgery? So jacked up, right? Get your blood boiling. Think about these things. They're real. All right, men diagnosed with prostate cancer. All right, so those who had surgery, of the 347 who had surgery, 16 eventually died of the prostate cancer, compared to 31 of the 348 men who did not have the surgery. So we're going to put this straight in the calculator, but I guess we'll answer some questions first. Was this an experiment or an observational study? So the key to an experiment, observational study, is we just observed whether or not people who chose to have the surgery, what their death rate was, and people who chose not to have the surgery, what their death rate was. That doesn't have any ethical issues. But you also, because you're allowing them to choose and not randomly assigning them, you could have some lurking variables and confounding, just because there would be an association. We cannot prove a causal relationship between having surgery and a lower death rate unless we had a carefully designed experiment. So we do have to have that element of forcing people to be a part of a randomly assigned treatment group, whether they like it or not. So that is something to discuss. Now, in this case, we did cross the ethical line, in my opinion, because we randomly assigned them to it. So they were randomly assigned to either undergo surgery or not undergo surgery. I don't want other people to make that decision for me. I want to make that decision, because America, freedom. All right. Was this an experiment or observation? So this is an experiment because of the random assignment treatment groups. That's how we know. Create 95% confidence interval. Let's do this thing. All right. So stat, test, beta, 2 portions Z interval. We're going to do the difference between the two groups. It doesn't actually matter which proportion we do first. So I'm just going to do 16. So I'm doing the surgery first. So 16 out of 347 and then 31 out of 348. All right, 95% confidence, go. All right, so we're saying the difference between these two should be the first one minus the second one. So the first one, oh, it'll give us the two proportions. So of those who had surgery, there we go. Why am I trying to do it in my head? Of those who had the surgery, it looks like 4.6% of them died. But of those who did not have the surgery, 9% of them died. So it almost doubled. You see what we just did? So these people who were told that they couldn't have the surgery, even if they wanted to, or even if they could pay for it, like with their own money, we just doubled their death rates. Do you want to be randomly assigned to that treatment group? I don't think so. Just think about these things. They're important. Okay, wow. I got to breathe in, breathe out. It's going to be okay. Getting all bent up out of shape. I'm the only one in my house. All right, so those are different sample sizes. The difference between these two is anywhere from negative 0.08 and negative 0.0058. Okay, so notice on this one, when we interpret intervals, our null hypothesis is that the difference is 0. So the question we have is 0 contained within the confidence interval? Both of these values are negative, so they're not, but barely. Okay, so there's a moment of caution here. That means that even though it doubled, it looks like it doubled. That's our best estimate from this. The death rate doubled when we didn't allow them to have surgery. It is really close to the margin of error. It's almost within the margin of error, which means we need to have a larger sample size, or the effect size between the difference between these two rates is not big enough. Now, if you told me I had a 4.6% chance of survival if I had surgery and a 9% chance of survival if I didn't have surgery, even if the surgery cost $200,000 or even $500,000, depending on how old I am, that's terrible. I might choose or might not choose to go ahead and have that surgery. But again, I think that choice should be on me and my future financial situation. All right. Your lives are priceless, by the way. I just wanted to let you know that. Okay, so yes, that's awesome. When we're looking at the difference between these two, 0 is not contained within the confidence interval, so we do actually have enough evidence. Now, this was a 95% confidence interval. Okay, clearly we would do a one-sided upper test because we want to make sure that you have a lower death rate if you're going to spend money to have a surgery. Okay, we don't care if it's different in the other direction. Obviously, if you are more likely to die from even if you had surgery, then it's not worth the money, right? Because we're spending money. We want to make sure it's not just different. We want to do a one-sided upper test in this case. And because it's entirely below 0, that means that we believe that there was a difference, and we want to reduce the death rate, by the way. That's like thinking in the negative or whatever. And so, yes, we would have enough. And if there was 95% confidence, then the alpha level we used, there was 2.5% on one tail, which is the one tail upper that we were interested in. So with a 2.5% false positive rate, we did have enough evidence to reject a null in favor of the alternative. So we believe that surgery is beneficial. Based on our confidence interval, is there evidence that surgery may be effective in preventing death from prostate cancer? Yes, because 0 is not contained within the confidence interval. With an alpha level of 2.5%, we're doing a one-tailed upper test. Now, just in case you're curious, I'm going to do the exact same thing, but run a 2-proportion z-test. And I want to make sure that the first proportion is strictly lower than the second proportion, because death rates, we want them to be lower, if that makes sense. And the first one was a surgery group. All right, so then hit calculate. So we are under there. Our p-value, we're in the 1.2 percentile. Sorry, the bottom 1.2 percentile. So it's technically, I suppose you could say a one-tailed lower test, but it gets confusing because we're dealing with death rates and we want to reduce death rates, not increase them. You get the idea. There's the difference between the proportions, same thing we got before. This will give us a pooled, so the overall death rate for all the people, regardless of whether they had surgery or not, for all the people with prostate cancer, are 2 different sample sizes. And the only time that we would have failed, see, it was really close, like it was kind of borderline. Between our 2.5% alpha level or significance level, this was definitely less than that, so that's why our confidence interval was below, where 0 was not contained. But if we had a stricter alpha level of 1%, which sometimes we do that with medical studies, we probably would also have a larger sample size. I'm just saying that. Then it wouldn't have passed, at least not this one. Maybe a different sample would have, because it is larger than 1%, the p-value. All right, so that's the only one I'm going to do with you. Sorry I drug that out a little bit. It is a review. Hopefully you guys were able to follow along with everything we went through, and I will see you guys next week for the test. So make sure you're caught up on your homework and all studied up, and I'll see you guys later.